Cooper-electron pairing is responsible for superconductivity at low temperatures in certain materials. In 1986, it was discovered that electrons could be forced to pair in point contacts at room temperature and will be demonstrated here. This meter circuit is a special design used to detect the Cooper pair electron bindings. The LM334 is a constant current source adjusted by the 100K rheostat for feeding a low current density into the micrometer mercury stage. The micrometer stage is the input to the transconductance 741 transistor circuit. A 10K fixed resistor is momentarily connected by a push-button switch to calibrate the LM334 current source at a 10K reading on the panel meter. The 100K rheostat in the output of the 741 is adjusted to make the meter read exactly full scale when the micrometer stage is open circuited. This rheostat forces the 741 to the rail at exactly full scale to protect the meter movement from pegging damage. Meters are built with mechanical damping to allow repeated full-scale deflection without damage. A small blob of mercury on the micrometer stage is drawn up into a nanowire by adjusting the micrometer setting. The resulting point contact develops a high electric field as the current flows from the bulk terminal. A high electric field of several kilovolts at the point forces electrons to pair into Cooper pairs at room temperature. The Cooper pair electrons are spin degenerate, that is, have opposite spin directions. This creates pairs at the lowest possible energy state, that is, the maximum expelled binding energy. It is the repeated pair formation expelling of a fixed binding energy that exhibits a quantum step resistance dissipation effect. The resistance indicated on the meter may be at any one of these quantum step resistances calibrated on the meter dial plate. Fortunately, when a step resistance is achieved, the meter reading can remain for several minutes unless the mercury stage is disturbed. Here's the dial plate calibration with only the step resistances indicated. If the dial reads any one of these resistances, one can be certain that Cooper pairs are continually being formed in a point contact. Quantum step resistance R in ohms equals Planck's constant H divided by 2 times the number of channels I. The dial reads any one of 8 channels. This is a meter assembly I described earlier, and dial calibrated to the 8 step resistances. Here I'm adding mercury to the stage. The micrometer. Now I'm calibrating for the meter to full scale and calibrating to the 10K calibration point. And we'll connect the stage back. Turn the meter on. Try to get a step resistance. Each one of these points is, if it sticks on one of these points, it's, you know, you're on a step. There, that's a 6.45 k ohm point. And it's hard to say, but this thing is 2.2 k ohm. 3.22 k ohm point. Those steps are pretty close, down at the lower end there. Calibration might be off a little bit on. And it does go from one step to the other You can see it starting to creep up to the other reading. You readjust the calibration a little more. There's 6.45 again, and it's gradually creeping up the ramp to the next step resistance, which is 12.9 k ohm. Takes a little while for the pairs to reassemble. Slow process, but it's going up. When it gets to 12.9, it should stay for a little while at that reading, so we know we're on a step resistance. Almost on the step. There's the 12.9. You see it's fairly stable there. So we know we're on a quantum step resistance. There are a large number of Cooper pairs being created at these points, and several million per second. It's starting to drift off the meter reading. It looks like 3.22 K again. Could creep up to the 4.3s. Quantum step resistance. Going back down now. It's very low current density, about 1.5 microamps being fed by the meter into this stage. And it's constant current, which means as the resistance changes, the voltage changes proportionately. And that's where you can read the resistance on the dial. But it goes from one plateau to the other. The current still is continuous. one plot to one step to the next. It's a minor miracle, really, because there's so many pairs being formed per second in that stage, Mercury stage. It's interesting to see nature work. In the last 50 years, during which the BCS theory for superconductivity has been accepted, there's been a mistaken belief that phonons and lattice effects cause Cooper pair electron bindings. Theorists ignored that electrons also have a magnetic moment in addition to their charge. In fact, electrons have the strongest magnetic moment of any subatomic particle. The electrical repelling force varies inversely as the square of the charge separation, but the magnetic attraction force varies inversely as the fourth power of the magnetic separation. We will show that it is the superior magnetic moment force in the near field that is responsible for the pairing of electrons and the cause for the quantum step resistances. Here we graph the forces, energies, as an electron approaches an electron and the electrons pair. In the left panel are two equations. PED is electrical potential energy, and PUXD is the magnetic potential energy. The D in the denominators of two equations are the separation of the PED charges and the separation of the magnetic moments in PUXD as they approach each other. These equations are here graphed to show the binding energy physics for electron pair formation. This physics explanation was first shown in my book published in 2008. The computer-generated graph illustrates that the electron's magnetic attraction force can be several orders of magnitude greater than the electric force repulsion in the near field. The PED red trace equation is the electrical potential energy in joule between electrons. The PUXD blue trace equation is the magnetic potential energy in joule between electrons. If we divide these equations by D, we get the forces in Newton, and one can readily see that D squared in the electric force and D to the fourth power is in the magnetic force. The green graph traces the difference between electric and magnetic forces and shows the electrons binding creates the binding energy as the force is null. As electric and magnetic force is null, a monoenergetic photon is created which radiates away the mass defect energy, holding electrons as a bound pair. The pair will remain bound until this missing mass energy can be replaced from the environment. At room temperature, this energy replacement occurs rapidly, releasing the electrons from pairing. At superconductive temperatures, however, the source for environmental energy is effectively shielded, and the superconductive currents result from the perpetually bound electrons. This room temperature electron pairing is exactly the physical mechanism with a strong force that holds a proton to proton, neutron to neutron, and proton to neutron in atomic nuclei. However, nuclei missing mass binding energy is much larger at room temperature making atomic structures stable. In the right side panel, the binding energy B times bond length D turns out to be a fundamental constant equal to charge squared divided by 4 pi times epsilon to 0, the vacuum permittivity. This product of binding energy times bond length has the dimensions of joule meter and holds for all bound subatomic particles in addition to the pairing of electrons. In the red block, we use this BED constant to calculate the quantum step resistance of one Cooper pair channel and obtain the exact expected value of 12,906.40377 ohms as proof of concepts. Here is shown the Cooper electron pair superconducting electron channels, showing how the possible binding of pairs would look like schematically. In A, the RK is linking electrons 1, 3, and 2, 4 pole to pole in the published von Kleisig resistance standard of 25,812.807 ohms. In A, the dipole to dipole Cooper pairs 1 to 2 and 3 to 4 are first formed and then are bound into the two parallel RK electron channels. In both A and B, the electrons first bind by expelling the binding energy and will remain bound into the superconducting electron channel as other pairs form unless the resulting missing binding energy can be replaced from the environment. Here we show the Planck constant in joule seconds derived from the universal binding energy Be times bond length D. The various step resistances shown on the meter dial plate are derived as 1 through 8 parallel channels of Cooper pairs.